Lewe and nuclear power. Imagine you're standing on the ground. Over your head there's a dome of reinforced concrete. A huge dome just of reinforced concrete. Now imagine it's just about to collapse. Look up and see if you can see where it's going to collapse. What you'll see is one point will twist out. The fracture will occur. You'll see like a twisting fracture as it collapses at a point, and it will be on the edge of the cap, so that a sphere is strong here where it's made of a spiral, and then the spiral becomes a cap, and the cap is strong, but the joint between the cap and the spiral, there's a transition on the curve of the sphere. It depends. That's what guides where this transition is. That's where the weakness is, and that will collapse. Can you see that? So what you then do is your design is you find that point of collapse and you put a prop there, and you don't let it collapse, and you design your structure such that it has sag in it. So you design the dome, you work out all the loadings that you need in there in your steel, you've designed it such with the steel that it allows it to collapse at this just infinitesimal degree we're talking about in terms of collapse. And you allow that sag in your design, and then what you do is you don't allow the sag to actually occur. You put a prop there so that the sag is exactly where it needs to be to hold that plastic zone in space-time, touching into gravity all the time. So changing the gravity of the locally and of the structure is the best way to think about it. So that's, if you think about Young's modulus inside the steel, you have an elastic zone, then it yields, and then there's another zone of plastic, they call it, which is even stronger, and it tails off. It gets strong and then it tails off. At the end of the point where it stops, it breaks. And it's that point where it breaks that Lewe is designing to, using the coefficient tables that are currently in the PCA document, which are currently still used in engineering practice today. And so it's a nuclear reaction. Literally a nuclear reaction is occurring inside that point in that structure. You then repeat looking at where these spirals are occurring, you design your structure, holding it up as a dome. You then take this whole design idea, you can then design flat ceilings with the same supports, with mushroom supports that are cast into it, and you'll see the influence lines of bending associated with this action, and you'll find exactly the same occurring, this plastic reaction. So you're standing on the motion rather than standing on where you should be in three-dimensional space when you're building a structure. That's why Lewe is nuclear energy, because once you've discovered that energy, and it works, these things stand up, you can then assess where this is, what energy you're getting from there, start investigating it, understand that it's connected to water, because you've designed it from a water tank, so your shape of your bending is imagining that the water is pushing at that point, so you've designed everything to suit a sphere of water, and then you corrupt it. And by corrupting it, you get the energy, bypassing the natural way that the energy should be here, keeping the planet at the proper speed. Because the penalty for using energy in this way is that you've brought mass energy from the inside of the planet to the outside and converted it into dead weight. And it's just slowing the planet's momentum. And that's Lewe, 1915. So physics is finished. Let's engineer. Let's get out of this problem. Because problem, it really is. If you look out at the world and you think, oh, what's going on? Physics is corrupt. Engineering is truth.